morning, everybody. My name is Amar Cruz.
Bernardo Valdez.
Salahuddin Antawadja.
Elena Collantes.
Summer Arevalo.
John Ho, Anthony Agasabian.
And together, we are Haavocc Robotics. First and foremost, I'd like to thank everybody for being here with us this morning. We know that everybody's time is precious, and we sincerely appreciate that you are all here with us today in this presentation. As a constellation, you will be the first to witness the unveiling of our premier product, Haavocc, the future of firefighting. Before we begin with the details of our project design, allow me first to describe a quick project background which led to the conception of Haavocc. Haavocc's design was geared towards San Diego State University's first firefighting robot competition to be held this afternoon in the engineering building at 4 p.m. San Diego State University's firefighting robot competition rules are as follows. Each team must create a robot that can autonomously navigate, locate, and extinguish a candle flame in the arena using 100 ml of water and any method of deployment, while avoiding decoys. The competition will take place in two phases. In phase one, each robot will traverse the arena independently, will be allowed 3 runs, and the best time decides the win. Deploying the firefighting agent on a decoy will terminate a run. In phase two, all robots will be competing simultaneously to make it a little bit more fun. Engaging other robots is allowed and is highly encouraged. The first one that puts out the candle flame obviously will win. To rise above all the competition, we decided to equip Haavocc with precision navigation, an advanced obstacle detection system, an advanced fire detection system, a state-of-the-art fire extinguishing method, and swift mobility. Now I will pass you over to Samer, who will go over the visually appealing yet very functional look that Haavocc has.
Thank you. Good morning, everyone. So to mark the start of our project, we needed to design a chassis that is going to contain all the components such as motors, wheels, sensors, and the firefighting system. So we designed a rectangular shaped chassis that is 9 inches in width and 13 inches in depth. We cut 2 sides in the chassis to fully contain and protect our wheels. And we also designed a rounded edge in the front that will facilitate the fire sensors in the process. So after we designed the chassis and after we determined where all the sensors are going to be located, we started the process of designing the wall covering of our system. So we designed a wall covering that will follow the contour shape of our chassis, and we extruded that wall 4 inches high. And as you see, we made a front cut that follows the round shape of our piece, and that will function as a window for our fire sensors to find the candle. And we also added extra spaces for sensors that will be discussed in the future slides. And as you notice, we also left the top of the wall empty. And the reason why we did that, because we wanted to have an easy access to the components that are within the robot. And after we finished this process, we started designing the covering process. And the covering process was done in 2 parts. The front part that contained a vertical wall that goes all the way to the bottom of the chassis. And the reason why we did that, because we wanted to protect all the electronics that are located in the front from the water that is in the firefighting engine in the back. And then we started designing the backside of the robot. And as you see, we had to elevate the backside to have enough room for our firefighting engine. And also, what's important about this part is the fact that it's very easy to remove. And the reason why we did that, because we will always need to access the firefighting engine to replace the CO2 and to fill the tank with water. And then after we started the assembly process, all the parts were assembled in a timely manner in parallel with the process of the hardware and software. So this is basically our finished product. The total dimension was 9 inches by 13 inches, and the total height, including the back part, was about 8 inches. Now I'll pass it on to Bernardo to speak about the block diagram.
Thank you, Samer. In order for all hardware to be able to communicate, we developed this simple system, this simple block diagram that will describe our system. Our system is being powered by a 14.8 lithium polymer battery, which then will be regulated to a 3.3 and 5 volt rail. Our brain cell for our motherboard is provided by a PIC32 microcontroller, which will be able to power our inputs and outputs and have a sophisticated algorithm system. On the left side of our motherboard is equipped with inputs, starting with the ultrasonic sensors that will detect and avoid any obstacles from the front. Our temperature sensor that will censor if it's a decoy or a candle. Our sharp IR sensors that will be mounted on the side in order to determine the wall distance of the arena. And an array of flame detectors that will home into our flame. Also on the bottom of our motherboard, we equipped it with a power LED to determine the status of our motherboard and LED arrays to determine the status of our robot. On the right side of our motherboard, we have all our outputs, starting with a switching circuit that will control a solenoid for a firefighting system. And lastly, our motor control drive that will power up our motors, which our motors are half encoders that will provide encoder feedback to our microcontroller in order to provide mobility. In order to describe more about mobility, I'll pass it over to Elena.
So for mobility, we had 3 goals. We wanted to achieve a max velocity of 2 feet per second. We also wanted to implement skid steering and also dead reckoning. So for our hardware, we used 2 motors with encoders, 3-inch wheels, and a dual motor driver carrier. So just with the hardware alone, we were able to achieve our max velocity as well as our skid steering. But in order to do our dead reckoning, we actually had to use our microcontroller to use an encoder feedback loop. We started off with our microcontroller receiving some initial values that we kind of guesstimated in order close to what we thought our velocity would be. We then feed that to our microcontroller, give it to our motor driver, give it to our motor, then it'll return encoder feedback to our microcontroller. We use a PID controller in order to adjust that value then in order to see if we need to speed up our motors or decrease the speed. We started off with just the p-value, the proportional value. It was pretty effective, but we needed a little bit more of a boost to be able to go at a constant velocity. We then added an integral value, and that helped a lot. That was a very big difference. And then we tried a derivative. It didn't make much of a difference, so we just chose to exclude it in general. The result of this feedback loop then gave us a robot that goes pretty straight, as shown in the short clip. So dead reckoning is a big part of our navigation, but we also have a variety of sensors that will help us further navigate through the core smart tech fleet. And now I have Amar explaining our sensors.
To be able to detect objects and avoid them in front of the robot, we wanted a sensor that has a wide enough sense width at a distance of 1 foot, such that in any case an object within the width of the robot is detected in front, we'll be able to make adjustments as necessary to steer away from it. For that, we found the LB Max Sonar EZ0 to be the perfect choice. With this sensor, we're able to implement what we needed with just one sensor because it was perfect for the application. Another sensor that we use are the IR sharp sensors for proximity along the sides of the robot. These sensors aid us in locating how far we are from the walls and looking for openings that we could turn into to enter rooms. For this particular sensor, we're looking for something that gives us at least a maximum range of 3.5 feet, because the hallway is approximately 7 foot wide, 7 foot in width. With a sensor with this range, we're able to detect both sides of the wall, even when we are, perfectly centered. Now, another sensor that we need to be able to navigate through the arena will be the flame sensor, which will be discussed by Salah.
So for this competition, we already know this is an enclosed arena, so we decided to detect the flame using 2 sensor systems. The first one is detecting the IR flames. This is the candle flame is the only source of IR. So to detect the IR flame, we use an IR photo transistor, which blocks out any light other than IR. And as the light approaches the transistor, the current flowing from the collector to the emitter varies. We're able to detect that voltage difference using a simple voltage drop, and we amplify that signal using a simple non-reverting op-amp system. Now, we went for a gain that will get us as close to 3.3 volts as close as 3.3 volts as we could get. So what we did is we set up an array of sensors, of 5 sensors, and for each sensor we went for 30 degrees for each sensor. Now we researched the sensors and we found out the results that we get as the angles widen. As you can see, the closer it is to the center of the angle, the stronger the signal. As far as close to the edge of the 30-degree edge, the signal decreases dramatically. But what we noticed is once we implemented it in reality, the ADC sensitivity readings was actually much stronger. So what we initially wanted was 150-degree angle detection was actually 180 degrees. And as you can see in the next slide, we have a pretty accurate position of sensitivity of the fire. We're able to detect it as it moves wherever the fire is on the thing. We'll be able to get it and we will adjust accordingly. Another sensor we're able to use is the temperature sensor. Now this temperature sensor is used so we could detect the difference between the flame and the decoys, which will be set throughout the map. Now this temperature sensor only has a 6-inch detection range, which does not give us much, but it's enough for us to be able to detect the difference between the decoy and the flame because our fire system is pretty strong enough to reach anything past 1 foot. Anything less than 1 foot. And to explain how all this hardware works using software, I'm going to pass it on to Elena to talk about the software architecture.
So our robot runs using a state machine. Starts off in an idle state where we have to push one of the buttons on the top in order to start it. This will then go to another state where we'll just set up the map. It'll set up some other variables that might have been used before or anything. We then go on to our navigate state where we use our dead reckoning. We use a pre-mapped of the course, and then we use our ultrasonic sensors, our proximity sensors in order to avoid any collision. We also use our IR photo transistors in order to be able to see if we can find a flame, which is the point of the thing, of the robot. We then, if we do find a flame, we go on to a fire detected state. Fire detected state. We also store the values of the map so we can find our location once again if it does happen to not be a flame. We go from the fire detected state where we center the flame. We follow the flame around and see if we can center it to the middle so that we can then spray it if needed. We then go to a verified state where we use the photo transistors once again in order to check the signal of the flame. The flame, the way it works, it changes very gradually. It doesn't have very big jolts in it. So that's how we verify our flame. If it happens to be a decoy, we then return to our route using the values that we had stored from the map before. We just kind of back up and go back to where we were. And if it is a fire, we then go to our fire extinguish state. We then spray the centered flame. The flame has already been centered, so we spray it with water. We use our photo transistors once again just to check, to verify that it has been put out. We use a temperature sensor as well to check that it has been put out. If it has, we then go back to our idle state and wait for another button push. Now we will have John that will explain how our fire extinguishing system works.
This is the lock diagram for our firefighting system with the CO2 cylinder controlled by 60 psi plus regulator. So when the CO2 discharged to a solenoid valve, it compresses the water tank and the water presses out the nozzle with the hose shape. So this is our firefighting system circuit that's used to control the solenoid valve. And then it's operated by a microcontroller. So when the flame detection sensor detects the fire, it will send a signal to a microcontroller. Then the microcontroller sends a short pulse signal to the base of the transistor. At this time, the switch is on, the solenoid valve is open. Then the CO2 discharges to the solenoid valve, then compress the water tank. The water presses out the nozzle. So this is our picture of firefighting system before and after we put in the back of the robot. And this firefighting system does puts out the candle. So now pass to Anthony for milestone.
Thanks, John. So this slide is a complete representation of the challenging milestones Haavocc Robotics has set forward for ourselves. As you can see here, everything's highlighted in green, indicating that we have met and accomplished every milestone we have set. But as we all know, no project runs perfectly, and there are always minor setbacks and delays. The minor setbacks and delays we had on some of the milestones are indicated with the red asterisks. But with a few minor hardware changes, we're able to overcome these challenges and minor setbacks, and it has brought us to where we're at today, and that is in having a fully functional firefighting robot. I would next like to jump into the budget. As you can see here, we have a pretty detailed pie graph indicating where Haavocc Robotics has allocated all of our money. We had a total of $750 that we were allowed to spend for this project. Haavocc Robotics ended up only spending $702. We stayed $48 underneath the budget while still maintaining a fully functional firefighting robot. I'd like to give it back to Amor Cruz to wrap things up with this presentation.
When first tasked with designing this firefighting robot for the competition, we at Haavocc Robotics saw this as an opportunity to advance firefighting robot in general. We did not only design a robot that can compete and rise above all the competitors, but design a robot with all the right features that can easily be upgraded to a version that can perform real firefighting tasks. We at Haavocc Robotics pictured Haavocc to one day be alongside our brave firefighters putting out fires out there. We envision Haavocc to be the future of firefighting. Thank you, everybody.